Our solutions for quiz 3 for Math 251. On this quiz, we're asked to find some derivatives. So here's a function, find its derivative. Had I asked you this a week ago, this would be the worst problem ever. You could probably do it using the definite. You could definitely do it using the definition of the derivative or the difference quotient, but it would take a good, I don't know, half an hour or so. It'd be a mess, huge algebraic mess. The nice thing is now that we have these rules, these derivative rules, this is actually pretty easy to figure out. F prime of x is just the derivative of 2x to the fifth minus 3x cubed. I'm going to show a lot of steps here. You don't have to show all these steps. In fact, you could probably jump straight to the final answer just looking at this thing. But to show you where it comes from, we have rules that say the derivative of a sum is the sum of the derivatives, meaning if I want to find the derivative of this big sum, a bunch of things added together, I can just find the derivative of each term individually and add those up together. And actually, if I want to find the derivative, well, I'm going to show a lot of steps. I don't know why I'm going to show so many steps. Maybe this is helpful for somebody. So you're taking the derivative of a bunch of stuff added up together. Instead, take the derivative of each of those individual things and add up all those derivatives. So how do I figure out the derivative of 2x to the fifth? Well, you can probably just look at it and tell that it's 10x to the fourth, but really what's going on there is I have this constant here, this 2, and I can pull that out in front. So it's 2 times the derivative of x to the fifth. And in this case, I have a negative 3 as my coefficient. I can pull that out in front. So it's negative 3 times the derivative of x to the third power. And similarly, the derivative of x, and finally the derivative of this constant out here, 141. And so now what I can do, all right, I'll do this for this one. I'm never going to do this again. Is I just have x raised up to a bunch of different powers. I have a power rule I can apply. The derivative of x to the fifth power is 5x to the fourth power. The derivative of x to the third power is 3x squared. The derivative of x squared is 2x to the first power if you want. The derivative of x is just 1, and the derivative of a constant is 0. And so I can simplify that a little bit and call it 10x to the fourth minus 9x squared plus 20x minus 1. And maybe I even put in a little comment that says don't need to show all work, to show all this work. Can if you want, you just don't need to. If you can look at this and tell that it's this, that's fine, I don't care. The point that I want to make is this is a hell of a lot easier now that we have all these different rules. So now do it again down here. You're like, I can't do it down here because, well, maybe you don't say that. Maybe you do, I don't know. Because this is a polynomial, this is not a polynomial. Like my rules kind of only work when I have x raised up to powers. Well, that actually is what you have here. It just doesn't look like it. Really what you're being asked is to find the derivative of 2x to the 1/2 power, because the square root of x is x to the 1/2, plus x raised up to the 4/3 power, because the cubed root of x to the fourth is really just x to the 4/3. And that's a derivative I can figure out. This is 2 times 1/2 x to the negative 1/2 plus 4/3 x to the 1/3. It's applying my power rule, taking the exponents and bringing them down in front, and then subtracting 1 from the exponents. 1/2 minus 1 is negative 1/2. 4/3 minus 1 is 1/3. And I can clean this up a little bit. I could call 2 times 1/2 is just 1. So I have x to the negative 1/2 plus maybe 4x to the 1/3 over 3 if you want. Another way you could write that is it's 1 over the square root of x plus 4 times the cubed root of x over 3. Any of these are fine. I don't care what form you leave it in, whether you use radical form or exponent form. As long as you get one of those as your answer, you're good, or something equivalent. All right, part C. Guess we're back to F's here. Fine. What do you do here? What do you have when you have stuff multiplied together or divided? Well, it turns out you use the product rule and the quotient rule. However, we haven't learned the product rule and the quotient rule yet, so we can't use them because we haven't learned them. So what we can do is we can rewrite this thing in a form that won't require the product rule or the quotient rule. So if I expanded out the top, if I multiplied these two binomials, FOILed if you want, I get x cubed minus 2x squared plus 3x squared minus 6x over x to the fourth. So what I want to do is find the derivative of that. Let me write that again. So f prime of x would be the derivative of x squared times x is x cubed. And then I got minus 2x squared plus 3x squared. So I have a net of 1x squared. And then I got minus 6x divided by x to the fourth power. But I still can't take this derivative without using the quotient rule, which I don't know yet. But what I can do is I can simplify this. X cubed divided by x to the fourth is x to the negative 1 power. X squared divided by x to the fourth is x to the negative 2 power. Negative 6x divided by x to the fourth is negative 6x to the negative third power. This is something I can take the derivative of. The way I take the derivative is using the power rule. Take the negative 1, bring it down in front. Subtract 1 from the exponent, you get negative 1x to the negative 2 power. Take the negative 2, bring it down in front. Subtract 1 from the exponent, negative 2x to the negative 3 power. Take the negative 3, bring it down in front. You get 18x to the negative 4 power. This is perfectly fine if you want to leave your answer like that. Another way of writing that is like this. Lots of other ways you can write it. I'll just choose those two and call either of those two an acceptable answer. But really anything similar, that's fine. Good enough? All right, last one. Suppose the graph below is the derivative, and f is a continuous function with its domain as negative infinity to infinity. Okay, so let me try this again. What I want to do is I want to change this question. So I'm going to give you a graph that looks like this. It's going to have open circles here and here. And this height is going to be, or this x value is 7. This x value is negative 1. And I'm going to label these points. I'm going to say at this point right here is 2, 0. And this point right here is 4, 0. And the domain of the function that we're trying to draw goes from negative 1 to 7, not including those 2 points. I think that'll make it easier to answer these questions. We didn't have to do all that, but I'm going to start you out with this picture. So anyways, if you were started out with this picture, and you were asked on what intervals is f increasing, you'd say f is increasing when the derivative is positive. And it looks like the derivative is positive from negative 1 up to 2, not including either of those 2 points. And then again from 4 up to 7. And I should label a couple more points because they'll be relevant. I'm going to call this guy right here the x-coordinate 3 and the y-coordinate is negative 2. And I'm going to say that this point right here, the x-coordinate is 5 and the y-coordinate is 1. Sure. I think with those points labeled, it'll be easier to answer all the questions. So this is my answer to the first question. That remains true. Wow, really good basketball game. On what intervals is f concave up? Well, f is concave up when the second derivative is positive. In other words, when the first derivative is increasing. So if you stare at this thing and you ask yourself the question, when is it increasing? Well, it's increasing from an x value of 3 up to an x value of 5. Everywhere else it's decreasing, so that would be my only answer. So the only spot where f is concave up is here. At what values does f have a local maximum? F has local max when f prime changes from positive to negative. Why is that true? Well, if the derivative is positive, the function's going up, it's increasing. So you're kind of picturing a graph that looks like this. And then it stops and it starts going negative. So if it switches from going up to going down, you kind of have that shape. So we must have been up at the top. We got a local maximum. So let's see where that happens on our graph. We want the derivative to change from positive to negative. Well, the derivative is positive out here, and then it's negative throughout here. It looks like at an x value of 2, the function's derivative changes from positive to negative, so we got a local maximum there. At what x value does f have a local maximum? God, I did a horrible job creating this. How about a local minimum? Well, f has a local min when f prime changes from negative to positive. Kind of the same argument, except backwards. If the derivative is negative, the function's going down. If it was going down and then it starts going up, that point where it switched from going down to up is a local minimum. So looking at our picture, the derivative is negative throughout here, but then it's positive here. At x equals 4, it switches. So I would say it has a local minimum at x equals 4. And I guess that's the end of this quiz.